Hey guys, how's it going? Steel Talk Sunday today. Gonna get into a few things kind of involving what a microstructure does. Not so much what the composition is, but what it does during heating and cooling, and try to lay it out in layman's terms. So, starting out, iron is made up of millions of crystals. So let's say that this bubble wrap, each one of these bubbles represents a crystal. Those crystals are called grains. Now, if we look at bubble wrap, we see that there's spaces in between each one of these little bubbles. There's spaces in between the grains. These are the grain boundaries. So, what do the grains look like? So in a 3D space, we all know what a cube looks like. And these colors don't mean anything, they're just there to show up on camera. So, we have an artist's rendition of a cube. And then each one of these... Hang on, I didn't make it quite 3D enough. You know, kind of like that. So we have our cube. When we heat the steel, it transitions into different phases. Now, think of a solution of salt, NaCl, or calcium carbide, or calcium chloride, or sodium chloride. When we dissolve these in water, that water is now a solution of salt solution. It now takes on, it can now take on different phases. So it can be ice, it can be a solid ice, it can be a liquid, or it can be slush in between that. So think about it like that. So starting out, we have our cube. When we have iron below 1670 degrees Fahrenheit, it is called an alpha iron. So, alpha iron. And this type of iron is ferritic or ferrite. So, alpha iron, or alpha, equals ferrite. You'll hear these terms. Ferrite just equals this. Actually, you'll mostly just see the A. Alpha iron equals ferrite. Okay? And this type of crystal is called a body-centered cubic. What does that mean? It means we have another cube and then we have our edges, but in the very center of this box we have everything is centered into that cube. Now when we heat iron up past or above 1670 degrees, iron is now in the gamma stage, which is this fucking stupid thing. And that equals Austenite. And we've heard these terms before. Ferrite, Austenite. They are different phases, if you will, of steel. So, what does the Austenite look like? That is a face-centered cube. So this is BCC. And then we have this, which is but on each one of the faces, we have an atom. Does that make sense? So they're all, each one is on the face. So it's called FCC, face-centered. And that's what these grains look like in in these two different phases, because there's actually three phases. There is no beta phase, because back in the day they thought there were going to be three, but then realized there's only two phases. And this is all carbon dependent, obviously. But I'm getting ahead of myself. So the more heat we add to ferrite, we get austenite. This type of thing forms at the grain boundaries. And what do I mean by that? So let's take this thing and zoom in on it, because it's a grain. And then we'll get like a representation. So we'll have a circle. And then we'll have alpha ferrite, and then we will heat it. And then we'll start to grow our austenite, or our gamma phase. And the reason why this whole thing will then turn into this is because we are growing, these grains are growing out over the ferrite. Okay, so we start with alpha, we heat it up, the grain boundaries, austenite starts to grow, and then we got the full austenite. So these are the phases of steel. Now there are actually three phases of steel. Like I said before, they thought that there was alpha, beta, gamma, but there's actually alpha, gamma, and then there's a third one with, and I'm kind of backtracking, but I'm kind of forwarding. So when we increase our carbon, we get to a point from 0 to 0.77% carbon. Once we get to this point, it equals this weird funny word called Euctoidal, or Euctoid. And this equals 0.77% carbon. Once we go past this point, so if we were to go 0.085, or let's do this. Let's go to 0.95, because this would equal a 1095 steel. because it has 95% carbon. Okay. We are going to, the steel is going to be called a Hypoeuctoid steel. And then anything below 0.77 is a Hypoeuctoid steel. Okay, now that we got hypo, and then we just have regular euctoid, and then we have hyper. Okay. That third one that we get is called Cementite. Okay. So now we have Ferrite, Austenite, Cementite, and it's all based off of the amount of carbon in a steel. So 0 to 0.77, we have hypo, and we have ferrite. And then from here to, let's say, 2%, we have hyper, and we get cementite. Okay? This one can contain this and this, and a third one called perlite. Does that make sense? So if we heated this up to its euctoidal point, it would contain ferrite in kind of like a different like, it looks kind of like this. It's like a little like striations or whatever. And then one of these is ferrite, and then one of these is cementite, and it just alternates. That's what happens with the euctoidal. Hypo, we heat it, we get we start with ferrite and we get austenite. This contains both, and then with hyper we start with cementite, and we heat it, we get austenite. When we cool this, when we cool this guy, we get perlite. These don't get perlite in them. These just get ferrite and cementite. Okay, I hope that kind of made sense. But basically we have the three classifications: euctoidal, which is 0.77% carbon; hypoeuctoidal, which is less than 77% carbon, 0.77% carbon; and hypereuctoidal is greater than 0.77% carbon. Okay, so to backtrack, we got alpha, gamma. These are what they look like. These are phases. And we also have cementite. Sorry. We start with ferrite. We austenitize. We get that austenite growing at the grain boundaries and then turns full austenite or gamma iron. Anything greater than the euctoidal stage, we get hypereuthoidal, and then we start to grow cementite. So that's going to look like this. Or I mean, we're going to grow austenite. So it's going to be CM, CM, CM. And then CM, CM, CM. Then we get our gamma. And we're heating up. And then we're getting full gamma. That's another phase. All right? So 3 phases: ferrite, austenite, cementite, blah, 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 blah. So once you cool it, or Sorry. So a hypo can cools to ferrite, okay? A hyper cools to cementite. And then euctoidal, like I said before, cools to perlite, which is a combination of ferrite and cementite. And these are two-phase grains that are thin plates of ferrite and cementite. Okay, and I'm not talking about cooling like quenching, because that's completely different. I'm talking about cooling from our 1670 degree temperature down to, you know, 1,000 degrees or something like that. So what does that look like? Glad you guys asked. It looks like this. Since most steels that we deal with knives are not gonna have a carbon content greater than 3 or 4%, I guess we can like get rid of that part. So it's gonna look more like this. Okay. Anything greater than over here, I think it's like cast iron. So right here is where our euctoidal point is. That says 0.8, but this is wrong. That's going to be that spot right here. That's where we're at 0.77%. And then we would heat it up. Obviously, that's going to turn that into a gamma. As we see, we have gamma, we have austenite. And then it's going to cool into perlite. Okay? Same thing over here. We have that hypoeuctoidal. It's going to heat up. And then we're going to get, at that point, we're going to get that gamma. It's going to start to grow along with that alpha, so that ferrite. And then it's going to grow so much it's going to get to here. Okay? So, and then with our hyper, same thing. We are, our ferrite is going to be Fe6C. And then that's plus this guy. That's what it's going to be over here. So we're heating up our 2%. And then we're going to be growing this austenite in the grain boundaries until we get to a point where we grow our austenite, or become full austenite, or what have you. Yeah, this should go up a little further, I think, maybe. Anyway, for right now, we're just worried about this. So at the temperatures which we're talking about, it's kind of like this. So since everything cools, everything heats up to one thing, austenite, everything cools to something different. So we have something we need to add to this chart because we need to represent the heating and cooling. So this is going to represent the heating. Okay. And then I think we can put another line right here. And then this is going to represent the other one. I know this is very confusing, but trust me, it's going to be okay. Yeah. So heating also, in some fucking, I think it's a French word, is chauffage? I have no idea how you pronounce that, but in this phase diagram, this first line is going to be AC3. What is that? That's austenite to ferrite. Okay, so Also, this line should probably extend up a little further. So that's austenite into ferrite and back and forth. Okay. And then we have, but this one is austenite into ferrite because, or ferrite into austenite because we're heating it. Okay. And then our next one is going to be, so then we have our normal A3 right here, which is the normal one. And then below that we have AR3. And then, so we're cooling down here. And that is another weird fucking French word that is Refroidissement hence why it has an R in it, and then this is hence why it has a C in it because of the shafaha and the yeah, that thing. So and then the AR3 is because we're dealing with a 3, which is the austenite. We're cooling from austenite to ferrite because our transfer goes, you know, back and forth. And then we have, and the reason why these are all 3 is because we're dealing with a Hypoeuctoidal steel. So then over here we're going to have ACCM because we are heating cementite into austenite, and then we have our CM and we are heating because of this fucking, the C's right here. And then this one is going to be ACM, and then yeah, and then we're going to do ARCM, sorry, ARCM here, because then we're going from, you know, this point down would be coming from austenite to cementite. And then we have one for perlite, which is just the normal, and all these are going to be drawn here. We have AC1, and then A1, and then AR1 for perlite. Looks super confusing. It's really not. Just think of this as like your base. The main black line is your base, and then we're heating up. The greater the carbon, the greater the carbon, the higher we go in our heating. Same thing with here. Obviously, this point is lower than this point. Yeah. These are important because we need to know how hot to heat everything and then how cool to cool everything to get that phase transformation. And that's, again, it's all based on the amount of carbon, you know. And then we get here, and then we've heated this up very, very like slight, or not slight in the terms of temperature, but then we're getting an alpha phase. We're turning this into ferrite here, and that's basically just 100% iron. At this point, it's going to be ferrite when we heat it up. And then obviously it'll get to a point where it gets to austenite, and then up here it gets into weird shit because we're actually melting the steel. Up here. Also over here. Sorta. So that's what it looks like. It's very, very confusing, I know, but that's what it looks like in this chart, in this iron carbide or carbon equilibrium diagram. So again, I guess we can draw an easier scale, maybe. How many more minutes do I have? Oh, I'm already at 25 minutes. Fuck that. We're not going to draw another scale. Just remember that hypoeuctoidal steels up to 0.77. Ferrite, Cementite, Perlite, and everything can heat or transform rather, into Austenite. Okay? Most of the seals we're dealing with are hypoeuctoidal, 1085 all the way up to, Rex 121. They're going to have way more carbon than any of these steels in knives, for the most part. They're going to be at least 95%. Well, I take that back. At least like 80% or higher. And we're going to see most of our transformations into cementite, most of our cooling transformations into cementite at those low high temperatures. And these are all above this. Okay? That we're not talking about quenching yet. Quenching is completely different. We would never cool to quench into martensite. This is like we're heating the steel and we're letting it cool, and we get transformation into cementite carbide. Then again, these are all different types of carbide. So it's the cementite carbide, perlite carbide, ferrite carbide. Austenite, I don't think it's a carbide because it's, I don't know, it's just different. All right, so next Steel Talk Sunday, we'll talk about these in relation to like quenching, what happens when we heat steel up to this phase, and so on and so forth. Hopefully it's not that confusing. To me, it took me a little bit to understand it, but I mean, if you guys have any questions, just reach out. That chart makes it really confusing. I think if you look at it, like anything lower than 0.77 ferrite, anything higher cementite, everything turns into austenite, and then this euctoidal point will always cool into perlite, which is, euctoidal means it can be two phases at once, which are those two phases is perlite. So if you understand that, then you got it. And that's Steel Talk Sunday. Thank you. Subscribe. Have a nice night.